Hello everyone, my name is Meek Patel and today I am going to discuss the role of artificial intelligence in chip design. So let us proceed. We are going to discuss the following contents: microprocessor and integrated circuit, how integrated circuits are manufactured from silicon up to the processor that is ready, the challenges that are faced in the traditional chip design and manufacturing, the role of AI in the semiconductor industry, the impact of artificial intelligence on chip design, and the challenges and limitations that AI possesses in chip design. We are also going to discuss the future trends and opportunities. So, let us first understand what a microprocessor is. It is made up of several ICs. IC is an integrated circuit that is a miniaturized electronic circuit that consists of multiple components such as transistor, resistor, capacitor, diodes integrated onto a small flat piece of semiconductor material that is typically silicon. A chip is the physical packaging, or we can say the actual piece of silicon that houses one or more integrated circuits. The term chip refers to small flat piece of semiconductor material that holds the IC. Chip design is the foundation of modern technology, driving innovation in computing, communication, and several other fields. It is important for us to understand the principles before discussing further. There are some following chips that are very popular, we can say. The first is microprocessor CPU chips that are the most commonly used among every single computer is made up of CPU. Then there is graphic processing unit typically used in gaming and AI. Then there are memory chips that store memory. Some examples are RAM, ROM, and flash memory. There is system of chips and also embedded chips. Now that we have known about what is an integrated chip, let us discuss how it is manufactured. The first process is water fabrication. This process begins with a silicon wafer, which is a thin slice of highly purified silicon, which is then subjected to a series of complex manufacturing steps. Then there are specification and requirements to every chip, which should be taken care of. They define the chip's functionality, performance target, power consumption, area constraints, and other key requirements. The architecture design of a chip is a high level blueprint of a chip. The logic of a chip is then decided with a logic design, which is done using a hardware description language, HDL. Some examples of HDLs are Verilog and VHDL, which are the popular ones. Then comes the part of verification and simulation. The design is verified through several simulations to check if the logic behaves as expected under various conditions. This process detects bugs and errors early. Formal verification techniques and test benches are used to validate correctness. Then, after the verification is done and the logic is validated, the logic is then further synthesized from a hardware description language to a actual net list of logic gates which can be implemented into an actual set of components that can be physically implemented onto an IC. We also have to take care of the power consumption and the timing requirements. They analyze critical paths to ensure that the signal propagates through the chip within the required time limit. Power analysis ensures that the chip stays within acceptable thermal and power consumption limit. Then, once all of these steps pass, the chip is then taped out. which means that the final design file is sent to the fabrication facility for production. Now, fabrication is the part where the integrated circuit, or we can say a chip, is printed onto a silicon wafer. It is it is done by using photolithography, where patterns are transferred onto wafer using light and photoresist. They define the shape of transistor and other circuit elements. Once the packaging and testing of wafer is complete to make sure that it works as intended, it is then packaged for deployment. We can see here a silicon wafer and a chip, and here is an Intel chip. Now that we have known the process of chip manufacturing, let us discuss the challenges in traditional chip design and manufacturing. It is a highly complex process and thus prone to various challenges and difficulties. Errors at any stage can lead to costly failures or delays, affecting performance, functionality, power efficiency, and manufacturability. Some of the problems are design complexity. A chip has billions and billions of resistors requiring intricate coordination between different components, CPU, memory, I/O, and to manage such complexity is extremely difficult. Even a small design flaw can cause the entire chip to malfunction, requiring redesign. Timing violations are also a problem. Timing violations can lead to data corruption, synchronization failures, or even the chip not working at its target clock speed, reducing performance. It is when a chip is not perfectly synchronized with timing when this issue occurs. There is also a big issue of power and heat management, where modern chips must be power efficient while also maintaining high performance. And the number of transistors, which is very high, leads to excessive power consumption and heat generation. Then, if we have also to discuss manufacturing defects. Let's say a design is perfect and the manufacturing process is begun. It can introduce defects such as imperfections in the silicon wafer, contamination, or etching errors during the photolithography process. Then there is also an issue of verification and testing. The chip must be thoroughly verified to ensure it works under all conditions, even though they are extremely difficult. And covering all the test cases is also a very tedious work. Then you also have to maintain a power versus performance trade off. What this means is that achieving the balance between high performance and low power consumption is very difficult, especially for mobile and embedded devices, where the performance requirements are very high, but on the other hand, you also have to consume less power and make them efficient. Then also there is issue of interdisciplinary collaboration because a chip design process involves multiple teams consisting of architects, logic designer, physical designer, verification engineers, and collaboration between this team is essential for the success. We can see a chip can be destroyed in such a process. Now that we have discussed the process of microprocessor and chip manufacturing and the problems in it, let us shift to the growing trend of artificial intelligence in semiconductor industry. AI driven tools can automate repetitive tasks and optimize circuit layouts. They improve the overall design efficiency. AI algorithms are also extremely good in accelerating and enhancing the verification process, ensuring that the chip functionality and reliability, and almost covering all the test cases. AI models can also predict chip performance characteristics, leading to better design decisions and reduced prototyping time. Now, let us discuss the impact that artificial intelligence has on chip design. The rapid advancement of artificial intelligence has significantly impacted chip design. AI algorithms are transforming the way engineers design, optimize, and verify microchips, leading to faster development cycle, enhanced performance, and more efficient power consumption. AI algorithms, particularly reinforcement learning and genetic algorithms, can explore the design space much faster and more efficiently than traditional methods. They can also identify optimal configuration and trade offs in a sorter type, helping to search for the best architecture configuration automatically, further optimize logic gates, and balance the power, performance, and area constraints. There is also an advantage of timing and power analysis. AI tools can predict potential timing violations and power issues by learning from the past models and design and using predictive models to analyze circuit. Machine learning models that are used for this process can predict timing violations very early in the design process so that we can solve them early on. They can suggest optimizations to reduce power consumption. They also analyze critical paths and then recommend design adjustment for a smooth flow. Accelerated verification and testing is also done using AI. It can automatically generate test cases based on the design characteristic and the past performances, covering more edge cases and scenario than traditional methods, possibly more edge cases. AI models can also predict where the faults are most likely to occur based on the past designs, helping to focus verification efforts on high risk areas. They can also assist in detecting bugs and even suggest fixes based on similar design issues from prior projects. They can they also enhance the performance modeling of the chip where the power consumption is better, the performance is better, and the enhanced modeling of heat dissipation and thermal performance ensures that your device works correctly. Generally, when manufacturing in chips, there is a high chance of fault detection in the manufacturing process. So AI can assist in that defect detection during the manufacturing or after it is made by using computer vision and machine learning models to inspect wafer and chips for defects faster and more accurately than human inspectors, predicting potential failures based on manufacturing data and adjusting the parameters in real time to reduce the defects. Here we can see that this is not the proper description of how AI will use, but it is a clue. AI assisted power versus performance trade off, where the AI algorithms optimize power performance trade offs by learning from past designs to predict how specific changes will impact the power and performance of future designs and suggesting an optimal configuration of voltage scaling, clock gating, and other techniques to reduce power without compromising on performance. So, AI does not design the chip for you, it does not do the whole process, but it helps you in detecting all the major flaws and errors that are present or could be made in the long process of manufacturing. It is really helpful in that. It can also be used to make the design of the chip more better, and better. It gathers data from several sources and from all the previous designs and then suggest a correctly optimized design, which a human would take more time to do. And also, it covers most of the edge cases and most of the design faults, which might not be possible with a human. Now, it has a lot of benefits, but there are also challenges and limitations to this process because the data requirements to do this is vast. Huge amount of data training is required, which is expensive and time consuming and hard to acquire. So much data and such versatility is very, very difficult. There's also an issue of interpretability where understanding the decision making process of AI models can be challenging, leading to difficulties in debugging and troubleshooting. Because if the AI makes mistake, you will have a hard time finding out what the mistake is. There are also security concerns to this because AI models are not that perfect. They are very much vulnerable to adversarial attacks, raising concerns about the security and reliability of them in this process. However, despite these flaws, they are nothing that cannot be fixed. And the future for AI is very bright. The future trends and opportunities for the artificial intelligence in the manufacturing process. And as we are talking about chips, the chip manufacturing process is huge. The future scope of AI based chip design is vast, with immense potential to reshape the semiconductor industry and unlock new levels of efficiency and innovation. Here are some key aspects of its future scope, along with how AI based chip design can be used for research purposes and market business perspective. You know, AI improves itself over and over, so they can be used in research purposes to make better chips, and they can also be used as a business perspective to know what is the best product in the market or what could be the next revolutionary product. Some of its implications are accelerating design cycles, optimizing beyond human capacity. AI optimization could be very, very, very perfect. AI driven co design of hardware and software, autonomous chip design, AI assisted verification and testing. As I said, they cover most of the edge cases and they are very good at finding faults. AI in design for manufacturability, they optimize the power efficiency and heat management, enabling AI designed AI chips, advancement in quantum chip design, enabling new chip architectures beyond the common von Neumann architecture, custom AI design for edge devices and IoT devices, also AI driven electronic design automation tools. The future for artificial intelligence is very, very bright, and it will certainly help in advancing our descent into new technologies and improving the further technologies. AI algorithms will be increasingly integrated into hardware as time passes on, which will lead to faster and more efficient designs. Machines will be integrated with AI, which will help fasten the design process and also make it more efficient. AI will also play a crucial role in developing chips for edge computing, enabling intelligent devices with on device processing. AI will be instrumental in developing quantum computers and their associated chips, which have the potential to revolutionize the field. So, as we have discussed, the quantum chips are very useful in our further advancement in research into technology and AI can help us a lot in that process. In conclusion, there is no doubt that artificial intelligence is going to revolutionize our world in many ways, and it's going to start or begin with the microprocessor and chip design takeover, and then slowly make its way to other fields. In short, AI will make our process faster, more efficient. It will improve our process, and it will be better than what currently is, hopefully. And lastly, thank you.